It gives me great pleasure to introduce today's keynote, Professor Dan Jones. He is a deep sea biologist and he heads up the Ocean Biogeoscience Group at NOC in Southampton. Dan is particularly interested in looking at temporal and spatial variability in deep sea ecosystems, and he also provides advice and thinks about how we can manage deep sea ecosystems. He's done that firstly with the oil and gas industry through the Serpent project, and over the last 10 years been working with deep sea mining in the Pacific and thinking about the environmental impact and providing policy on that. So without further ado, I'll hand over to Dan.
Thanks very much, Rachel. And also, I must say thanks to the local organising committee for inviting me here and supporting my visit to SAMS, for hosting this amazing meeting, and also for all of your assistance in making this happen and providing me the opportunity to speak today. So, I'm Daniel Jones. I'm going to be talking about disturbance in the deep sea. So I'm going to be bringing a more of a benthic perspective on yesterday's more pelagic keynote. And I'm going to be talking about how disturbance can be a force for ecosystem establishment, but also a force for elimination of ecosystems. And I'm going to be trying to talk a bit about that balance today. So, when you think of disturbance in the deep ocean, I think many of our first thoughts goes to the sort of global effects of climate change, and we've seen that there's impacts on oxygenation, on temperature, pH, food supply, which propagate down to the deep sea. And these impacts are obviously very broad in scale, very disruptive. And then perhaps the next thing one thinks of are sort of accidents, major impacts to deep ocean environments like the Deepwater Horizon blowout, which released about 5 million barrels of oil into the deep ocean and caused catastrophic effects to the communities there, at least in the short term. And then perhaps we think of natural resource extraction, taking out of deep sea fish, such as the orange roughy in this picture. And perhaps the new kid on the block is deep sea mining, or at least the thing that we're perhaps most concerned around at the moment. And I'm going to be using deep sea mining in my talk as an example of how we can understand disturbance effects and how we can characterize the natural conditions in the environment which are essential to detect disturbance, how we can understand what the impacts of a disturbance are in these remote deep sea environments, and look at recovery of these ecosystems, the time and space it takes for these systems to recover. And then I'm going to sort of end the presentation by talking a little bit about what we can actually do about these deep sea disturbances, how we as ocean scientists can actually interact with the processes and try and limit the impacts of these on a global scale and make sure that these fragile ecosystems are protected for as long as possible. So I'm going to start with some classic deep sea ecology theory to begin. And this really states that actually disturbance can be beneficial and is actually essential in developing deep sea ecosystems and their diversity. And pretty much since the days of the Challenger, when we moved from thinking that deep sea ecosystems were barren, lifeless deserts, to suddenly realizing that there was this wonderful array of exciting and unusual animals living in these environments, we've started to understand more and more about these systems and try and understand that actually they're hosting a very large array of deep sea species. And this sort of provides a bit of a paradox where you have a low food supply, essentially homogeneous in their eyes environment, but maintaining this high diversity of species. And the first theories around this sort of coincided with the quantification of species diversity sort of 50, 60 years ago. And they invoked these theories of equilibrium explanations where these benign environments as they thought were able to support more and more niche diversification, and these very narrow niches were able to support lots of different species. And that's perhaps true at an evolutionary timescale, but I think it was quickly realised that the environment was more dynamic than this initial thought. And these disequilibrium processes were proposed. And this invokes disturbance at various scales to try and support different species. And there's lots of different ways that this can happen, but it can lead from things like biological disturbance, bioturbation, movement of sediments by animals, cropping, and this supports a range of different animals that live in these different disturbance regimes. Physical processes are also important, current movement, for example, and as are episodic events related to resource falls. So, for example, if you see the episodic pulse of phytodetritus, that can be a disturbance to some systems, which results in more animals being able to take advantage of this and more different species being able to be supported. And we see examples of that at many scales, from phytoplankton over very broad scales to individual fish or whale carcasses landing on the seafloor, creating a very different environment on a local scale. And it was also critical to realise that these disturbance-related impacts on biodiversity fall very much within a kind of a Goldilocks zone. You need a little bit of disturbance, but not too much disturbance. There's too much disturbance in space and time leads to negative effects in many ecosystems. And this intermediate disturbance hypothesis has sort of been ongoing since the 70s as a means of thinking about this. And I think perhaps the reality is that you end up with this sort of patch mosaic of different successional stages or through stochastic processes which are supported by disturbance and recovery processes over a broader scale. And these support a large biodiversity at the scale of habitats, landscapes, ocean basins, which is really important. So ultimately, disturbance does have a role, and a positive role, in maintaining biodiversity. But disturbance takes many forms. It ranges from very small-scale local disturbances, like a holothurian knocking into some sediment, through to very broad-scale long-term processes. And those different levels of disturbance occur in nature, from bioturbation to tectonic processes and geological climate change. They occur in anthropogenic processes as well, so ranging from relatively small-scale disturbances through to much larger from climate change, for example. And the animals themselves, they respond in different ways too. So at a small scale, you may have an animal that just moves away from a disturbance, has a physiological response, which is very easy to recover from, through to ecosystem collapse and mass extinction at the worst end. We've seen through a lot of efforts to try and understand what the position is now that there's actually a lot of disturbance already happening in the open ocean. And this was an attempt to characterise what the cumulative impacts occurring in the surface ocean are in the year 2013. And you can see there's, from the intensity of the impact score, there's impacts happening across the world. They're happening throughout the ocean environment from a whole range of different sources. And these impacts propagate down into the deep sea. And we've seen examples in the presentations yesterday of things like microplastics occurring in deep sea sediments in really remote areas. And there's lots of other examples of the persistent effects of anthropogenic influences in these remote deep ocean environments. We also need to think about how they recover from deep sea disturbance, particularly when and I think the picture we're seeing is that these cycles of disruption and recovery are very much the typical state of affairs, and they were prior to our influence on the deep ocean environment. But as we're increasing the frequency and the duration of these disturbances, we need to try and understand what these deep ocean communities, and others of course as well, how they respond to these impacts. And we're particularly concerned for the deep ocean because of the high sensitivity of these communities to disturbance and potentially for the slow recovery rates. And this is from a number of perspectives. So we see that they live in an environment with low temperatures and low food supply, which leads to low biological rate processes. And this in turn leads to life history traits that are not helpful for recovery from regular disturbances, like low fecundity, long generation times, those kind of things. And also many deep sea habitats are those that are thought to be slow to recover and seen from shallow water environments to be slow to recover. So fine-grained sediments, for example, these large biogenic habitats that take a long time to form. And thinking about where we are, and scientists from SAMS, John Gage, an eminent deep-sea biologist, unfortunately no longer with us, who was at SAMS, was thinking about how we, as a community, go about understanding more about deep-sea disturbance and how diversity is influenced and maintained or destroyed by these processes. And he thought that in his textbook with Paul Tyler, that one of the ways that we can do that is by understanding anthropogenic processes and using those processes to, as experiments to understand better how biodiversity and communities respond to these impacts. And one of the ones he used as an example was deep sea mining. Understanding disturbance, of course, is interesting from a scientific perspective, but it's also a really important area to research in general terms. This scientific understanding will eventually, hopefully, lead to prediction, so we'll be able to predict what the impacts are of specific activities that we're carrying out. And then hopefully this will feed directly into management and decision making so that we can mitigate or reduce the impacts of disturbance in these environments. We can plan for industries that have reduced impact than they would have otherwise. And that's really important, particularly as we increase the frequency of disturbance in these deep ocean environments. So how do you assess disturbance? So this is the same in any environment, but equally applicable to the deep sea. So typically in an environment, if you measure some ecological parameter, and that could be anything from the health of an individual organism to the size of a population, through to some measure of the community, like diversity or community structure, you see that in a normal conditions, there's natural processes that lead to variability, but there's sort of a generally stable level of any one parameter. And then all of a sudden you get an impact on this system, and often that leads to negative changes, and these can be quite large. Sometimes they're positive too, but in this simplistic example they're negative, and that leads to an ecological effect, sometimes called the ecological resistance of that community. Hopefully, over time, things recover, and then you get back to this sort of stable baseline. Of course, in reality, it doesn't always go as planned, and sometimes the communities don't recover back to the original state, and you get to an altered state. Sometimes the communities that are not disturbed are changing as well, and we're seeing this particularly with climate change, that the control conditions are changing. So it's really important to understand the baseline, its variability, and as well how natural communities, unimpacted communities, change over time. And there's sort of three key processes that are essential to really understand what disturbance looks like. So this understanding of the baseline, the pre-disturbance and the control, the understanding of the initial effects of disturbance, and then this recovery time. All of these are somewhat unknown in many deep ocean environments. And in the case of deep sea mining, the Pacific abyss, far from land, is very poorly known, but we are increasing. We're talking about, I haven't yet, but we're talking for deep sea nodule mining about deploying these enormous machines to hoover up these nodule resources on the seafloor, which are scattered over the sediment surface. This is an example from the metals company made by All Seas. You can see the people for scale. And it should be noted that these test mining bits of equipment are scale models. They're not the full size. They're talking about using machines that could be 8 or even 10 times the size of these in reality when they go to deep sea mining. So it could be quite a large scale disturbance event on the seafloor. And I'm going to show how we can better understand these ecosystems of deep sea mining interest and looking at their impacts, and also show that how the UK as a marine science community has contributed, I would say, disproportionately positively to this knowledge, and it's something we should be really proud of as a community. I probably don't need to introduce the location of the Clarion-Clipperton Zone in the Pacific between Hawaii and Mexico, and this area that's roughly the width of Europe is the area of most interest for deep sea nodule mining. It is enormous, but the mining interests are somewhat concentrated, particularly in the eastern area, although there are claims throughout the area. I'm going to rather gratuitously use our wonderful pictures from a recent expedition we had to the Clarion-Clipperton Zone through the SmartX project to introduce the sort of phases of my talk. So I'm going to start looking at how we've understood a bit more about the natural conditions of this ecosystem. So the first sampling, as a theme that's running through this conference, was actually done by the Challenger about 150 years ago, which collected examples of the nodules themselves, which actually stirred more interest in the biology in many cases, disappointingly I might think, but they were inspired by these mineral resources on the ocean floor. And the potential even was noted for providing minerals that could be useful for humans. There was quite a long pause before a huge amount more activity took place, but commercial interest began really with the publication of the mineral resources of the sea in the 60s, and then quite quickly there was quite an array of expeditions to that environment to try and understand the mineral resources, but also to start to understand the environmental baseline, because it was recognised quite quickly that there could be some impact from this. The potential for these broad-scale impacts associated with mining activities was partly behind the formation of the United Nations Convention on the Law of the Sea in 1982, and then eventually the formation of the International Seabed Authority. They quickly got to work, started issuing the first contracts for exploration, and then tried to understand more about the environment, producing a regional environmental management plan, and now we're starting to see the first environmental impact assessments for actually carrying out disturbances in the deep sea. First of all, for exploration activities associated with collector testing, and soon, I suspect next year, we might see the first environmental impact assessment for actual exploitation activities in the CCZ. Associated with all this activity, there's been an uptick in the amount of marine scientific research as well, particularly since about 2010. And you can see this quite clearly on this graph produced by Muriel Rabone at the Natural History Museum. But this is about taxonomy, but actually the patterns hold for many other disciplines as well, in that you can see the number of species descriptions, also the number of publications about species in the Clarion-Clipperton Zone. You can see this uptick around 2010, of which UK scientists have been quite instrumental to. And this sort of illustrates the process. All of this exploration brings with it new science. When you plot the distribution of known species in the CCZ, there's actually quite good coverage at this scale. Admittedly, it's a large proportion of the world we're looking at, but nonetheless, there's still quite a few species discovered. Of all those samples, there's only just over 400 species that have actually been named, but over 5,000 species which we know are different but don't yet have names, which means that we're sort of about 90% of the animals that we encounter are undescribed. So that puts us in a good place for really understanding the impact. We don't even know what these animals actually are. This is compounded by the situation, or the ecology of the Clarion-Clipperton Zone. This is a sort of typical shot of the seafloor. You don't see animals everywhere. There's very low densities of animals. There are a few megafaunal animals hiding here, and I know there's a lot of people in the audience that will be able to pick them out very quickly. And there's lots of, obviously, smaller animals living within the sediments and nodules, but they're still maintaining a high diversity within these environments. And this gives you an idea. There's a sponge stalk colonised by a range of megafaunal animals, which you can find on occasion. And there's lots of ecological interactions. There's a sponge, tube worms, hydroids, and this beautiful sea star living on this once dead sponge. You see interactions between other animals as well. Many of these are completely unknown. This is a sea urchin with these crustaceans living in amongst the spines, probably both new species and certainly an unknown interaction that we spotted with the ROV. You see that many species need to use the hard substratum, so they need to use the nodules, they need to use this resource that we're going to specifically to remove from the environment. So this is an example of a crinoid that's currently being investigated at the Natural History Museum by Hugh, who's I think in the audience. We also see animals living within the nodules. This Neanthes polychaete is living within a nodule environment. We see lots of other animals, the foraminifera, are common on these nodules as well, and we see animals living around the nodules in the sediments. So there's a whole range of things that are dependent on having this hard substratum in the environment. It's not just nodules. We see some of these animals living on other areas as well. So this is a rocky outcrop, a really interesting rock formation, by the way. I'm not quite sure what it is, so if anyone's got any ideas, be welcome to hear them. But there's some anemones and sponges and all sorts of stuff living on these rocks as well, and some overlap of communities with the nodules. Beth yesterday introduced some work around the different nodule types, and we see that different nodule types have different communities associated with them. So these very dense small nodules, which are the target of mining, at least in Norrie D, have quite different communities from this more sparsely distributed large nodules. But they have similar communities consistently over areas of tens of kilometres. We even see these associations with nodules at the micro scale. So this is a time-lapse image. It's not very well reproduced, sorry, but it's what Loic van Orgenhagen at NOC has done is follow the distribution of animals as they're moving around on a day-by-day basis. And you can see that some animals, like the polychaete in green, very carefully manages to avoid the nodules, so it makes a path across the environment, avoiding nodules. The mollusk in yellow consciously seeks out nodules and only moves from nodule to nodule. And some animals, like these big holothurians in purple, just don't care and they go right through the middle of it. So we see these microscale patterns, which will inevitably lead to other things going on. We see relationships between the size of the nodules and the body size of animals as well. So we can suggest that the larger, long-lived, perhaps more reproductively capable animals are living on the bigger nodules and the bigger nodule patches. These individual level processes add up to community level changes. And we see differences in density and diversity of these organisms at different densities of nodule habitat, particularly when we move from very low nodule cover or no nodule cover through to having some nodules. There are quite big differences in the communities. These start to level off in the few studies we've got on megafauna, the bigger animals that you can sort of see as you look in the environment, and the macrofauna. They start to level off at sort of densities of 20 or 30% nodules on the seafloor. We also see patterns at broader spatial scale. So if we look at the landscape scale, we have the Clarion-Clipperton zone's not flat. It's quite actually far from it. It's much more of a rolling hill landscape. It's a bit like sort of around Southampton, actually, with these sort of few 100-metre high maximum hills. And then occasionally these larger seamounts. And we know that the seamounts have a distinct fauna. Perhaps that's a bit more obvious. But we also have seen distinct fauna in the hills. We see that the hilltops have a different fauna from the valleys as well. So even these sort of small changes lead to differences. And all of these, again, impact the way we understand disturbance. So where the mining takes place will influence the communities that it interacts with. We see regional scale patterns too, and actually this was highlighted yesterday in the phytoplankton, but productivity regimes also propagate down to the deep sea floor. And from what we can see, the data that we have at the moment suggests that the POC flux, the flux of this organic matter from the surface, also leads to changes in the density of these deep sea communities. We can see that at a broad scale. There may be other things controlling it. We probably need to do a lot more research to really understand it, but that does seem to be a consistent pattern. We've also seen, by compiling large numbers of these observations, actually many of them made during exploration activities, we've seen that we can start to understand these sort of broader scale regional patterns. And this recent paper published by Eric Simon-Ledo last year showed a major biogeographic boundary in the Clarion-Clipperton zone, separating the eastern from the western side, and with quite different communities, which we think is associated with the carbonate compensation horizon in that environment. So we're seeing big changes that are resulting from things that we weren't really expecting from the biological point of view. We see evidence of these stochastic processes, so these episodic food falls, which we talked about in a kind of classic ecology. They're happening on the seafloor in the CCZ. We see falls of Pleuroncodes, this pelagic red crab, arriving at the seafloor in their thousands, creating a resource for the communities. We see pyrosomes, even argonauts, is a wonderful pelagic octopus arriving on the seafloor and providing food and potentially even calcium carbonate to the organisms in this environment. We also know that the Clarion-Clipperton zone and the Pacific generally is an area of natural variability. We know there's climate-derived variability with the ENSO events that are happening, cycling multiple years. We know that there's seasonal variability in the food supply, at least from the phytoplankton and above, and that seems to propagate down to the seafloor. And we've also seen through moorings on the seafloor, so Dima Olenik, who's in the audience, has looked at the current events that are happening on the seafloor in this remote area, and you're seeing these tidal-induced patterns, but you're also seeing the influence of these mesoscale eddies on the surface that are propagating all the way down to the deep seafloor, causing high current events and likely interacting with the seafloor environment in terms of the biology. With all this temporal variability, we're guessing there must be some variability in the deep sea biology. We know there is in other deep sea areas, abyssal areas off closer to the Pacific coast of the US, and we're expecting to see them in the CCZ. We haven't really got the data, although we will do very shortly. And we also see that this idea of a shifting baseline is very likely to be happening. So Qilin Wei produced this plot which shows the time of emergence. So when we exceed historic variability in oxygen, pH, food supply, and temperature on the seafloor of the Clarion-Clipperton zone, you can see the mining areas overlaid to give you a feel for where you are. But we're already in a situation where we're predicted to be exceeding natural variability in some areas about now, which is rather terrifying, but it just goes to show. And even the majority of the area will be likely to be changed according to the models within this century. So with this shifting baseline, it's also important to consider when we're trying to understand disturbance. So what do we know about the disturbance effects themselves? There's a lot of different types of disturbance associated with deep sea mining. I'm going to focus on the stuff that's happening at the seafloor with these collector or mining vehicles as they move around and collect nodules. But there's a whole range of other processes throughout the water column, from the surface ships through to discharge plumes that are generated as a result of post-processing of the nodules. And we expect, from theory, that these animals in the CCZ are likely to be quite highly disturbed from activities. We know that there's a high rarity. They've got the slow life histories. They're used to generally stable physical conditions, at least compared to shallow waters, and they've got low natural disturbance. But we were also talking about a system that's very large. It's got few barriers to connectivity, from what we think. And we do see, at least from the limited evidence, that we have quite good connectivity in some of the fauna that we looked at. But we need to make more of these observations. So it's very difficult to make these observations, but we have made some quite good attempts. So first of all, we carried out a whole range of experiments on the seafloor that have been done either as a result of, accidentally as a result of attempts to understand mining processes, or purposefully to try and understand disturbance. So we see examples like Disco, where they towed a plough across the seafloor in the Peru Basin, and a whole range of other experiments looking at plumes. And there's a timeline of these experiments that extends back from the 70s to now, and several of these have been investigated in quite a lot of detail. They have their issues. Many of them are not representative of deep-sea mining. And most of them also were done a long time ago, and techniques have moved on quite a lot. So our understanding of the initial impacts are not quite so clear from some of these older experiments, but they still have some value. When we look at the immediate impacts, perhaps it's most useful to look at the modern disturbance experiments. So these have been done, there's a few examples. This one is carried out by the metals company last year, and they spent a huge amount of money trying to understand what the impact was on the seafloor, and employed a range of scientists from many disciplines to try and understand it. They first started by just driving the machine around on the seafloor, and this is a photo of the seafloor. Then you can see these caterpillar tracks lead to what you'd expect, a big track across the seafloor, and you can see the high-density nodules either side of them. Once the system becomes operational and they start actually harvesting nodules, it creates a much more extensive plume on the seafloor, and you can see the impacts here. So you can see the tracks, and you can see the areas that are covered by sediments from the plume generated by these mining vehicles. The plumes generated are quite extensive. This is an example from a different test, the test of the Patania vehicle, and gives you a feel for the amount of sedimentation produced as these vehicles traverse across the seafloor. And this is becoming actually relatively well known, both in observations and in terms of modelling the distribution of these sediments, and actually has really transformed our understanding of the behaviour of sediment plumes close to the seafloor associated with mining vehicles. Actually, for the better, it's in the sense that it's reducing the extent and the duration of these plumes beyond what we thought. And so the group at MIT have done a huge amount of work, and others, in trying to understand the sediment distribution. When you look at how this impacts the seafloor, this is some work that's been carried out by several of you in the room working at NOC, looking at some of the impacts of the metals company experiment, and you can see a range of different impacts as you move away from the collector vehicles, from complete smothering of nodules through to areas that are sort of largely clear within around a kilometre away from the mining vehicle. We're trying to understand what those effects of those plume events are, but we still haven't finished the analysis, and we don't have the data yet, so I can't present it. But what I can present is the results of a meta-analysis that we carried out a few years ago, trying to bring in all the results from all these early disturbance experiments and put them on the same scale. So this chart shows the differences from control in units of the standard deviations away from the control conditions. So we're seeing that most of the deep-sea mining experiments have an initial impact that's 1 or 2 levels of natural variability beyond the control in most examples. We do see that, so this collective disturbances is having a clear negative effect. We do see that the experiments that looked at the plume only and not the disturbance from the vehicle itself seem to have a reduced effect, and in some cases were sort of close to zero. So we're starting to see that a difference between direct physical disturbance of the seafloor and this resedimentation of the plumes. This is something that's really interesting, because if the plumes do have a big disturbance effect, that obviously extends the extent of those impacts quite a long way. But we'll have a huge amount more data soon once the results of the Britannia 2 test come out. We've started to see some even in the sessions yesterday, and from this metals company collector test as well. If you look a bit longer term than the initial impacts, you also start to see these changes are very persistent. At least the physical changes are persistent. If you go back to these sites after years and years of being left alone, they still look much the same. This is the Discol site, where you can still see the marks made by the plough on the seafloor after at least 20 years. In the Clarion-Clipperton zone, this is an example 37 years after an epibenthic sled passed through the seafloor, so not a mining machine, but actually a scientific collecting device. And you can still see that this epibenthic sled track is very similar to it was compared to the control conditions, which look like your sort of typical Clarion-Clipperton zone shot. So we're seeing this physical changes are still persistent over many decades. If you look at the biological changes, again through meta-analysis techniques, you can see if you try and plot the changes, at least in density and diversity against a recovery time, things are all over the place. Animals are recovering at different rates. Trying to see some patterns in amongst this data, which is quite tricky, suggests that the smaller size classes of animals, as perhaps you'd expect, respond more quickly and recover more quickly from disturbance activities. We also see differences in habits and traits, so we see that motile animals can recover more quickly than sessile animals, which is perhaps obvious, but starting to emerge from the data. But in all cases, the communities remain different between these disturbed sites and the control conditions, even after several decades, up to about 30 years at the moment. So one of the best sites is the Discol site in the Peru Basin, so not the CCZ, but also an abyssal site with nodules. And there a very comprehensive assessment was carried out as part of the JPI Oceans programme. And you can see quite clearly the impacts of the plough on the seafloor. So again, not a mining machine, a plough, but had some effects. You can see it has persistent impacts on dissolved oxygen and other sort of more functional processes around the ecosystem. You can see that density and diversity are still depressed in the track after 26 years. And those impacts extend for several tens of meters, even to over 100 meters away from those tracks in many cases. And when you try and model the impacts of these different disturbances, or the disturbance event on different processes, you see that the predictions for recovery back to some sort of similar state to normal are in the orders of many decades, if not centuries, before these ecosystems start to get back, even in sort of more basic functional measurements to what it was like before. One of the issues with the Discol disturbance event was A, it's not in the Clarion-Clipperton zone, and B, it wasn't a mining machine. And one of our best examples of an old test of a deep-sea mining machine was this OMCO collector vehicle that was tested in 1979 by a consortium that included Lockheed Martin. And they tested this mining machine. You can just about see a person here for scale, so it's a big thing, similar sort of scale to the modern ones. Quite similar in processes to the way that the modern mining machines are designed. Big difference is it was propelled by Archimedes screws rather than tracks. But this was deployed and carried out a mining test in 1979, which we went back to as part of the SmartX project in 2023. We were able to find the tracks, we were able to map them, and we were starting to look at some of the responses to that disturbance event and how the ecosystems are recovering. And to cherry pick one particular result in the megafaunal community, so the photographically derived fauna, we can see that there's still very depressed densities in the track site. The plume, interestingly, has increased densities compared to other areas, and the control and the pre-disturbance conditions, we have photos from 1978, also show sort of somewhat intermediate levels. So to summarise, negative effects from initial disturbance, perhaps obvious, but natural recovery is very, very slow and takes at least decades, probably centuries, probably longer. But we have huge levels of uncertainty on the effects, particularly the full-scale effects. So if you're talking about a real mining event where big mining machines will be operated for years on end continuously. And it's likely very dependent on the way that these are operated and the extent of the operations. There's lots of knowledge gaps. I haven't got time to go into them, but there's lots of things we need to know, and there's priorities for research. But I'm keen to get on to talking about what we can actually do about it. And as marine scientists, I think we do play an important role in this, perhaps more than we try and envisage. So I'll try and lay out what I think we can do as a community and provide some examples of how we've tried to do that. So the first thing is trying to understand how we can mitigate or reduce disturbance. So this diagram is a commonly used tool for understanding how you mitigate disturbance in the terrestrial world, for example. And you start with avoiding, so you can set aside areas that are not impacted by mining as reserve areas, so that provide propagules and connectivity to these areas to support quick recovery. And we started to do that. So there's, through the environmental management plan for the Clarion-Clipperton zone, there are set aside areas of particular environmental interest. Not necessarily interesting in most cases, we don't know what's there, but at least they provide some sort of reserve. And these were derived from scientific evidence. We've also seen efforts to minimise disturbance. This is a concept drawing from the metals company showing a collector with a shroud that collects all of these plumes and makes it wonderful and clean, and it means that we can reduce the impacts of mining disturbance. And there's lots of research that we can do around the effectiveness of that, what we should concentrate on, what the engineers need to prioritise in when they're designing these vehicles to try and reduce the impacts. The other two levels of the mitigation hierarchy, restoration, which we're probably familiar of from efforts on land, and offsetting, where you effectively restore an area separate from the area impacted, are problematic in the deep sea. This is a wilderness area, and we've argued that we shouldn't try and do these two in deep sea environments, or if we do, we need to be very careful about how we do them so we don't lead to unintended consequences. I think restoration does offer some potential. Potentially with nodules it's a bit harder, but we need to be very careful, and it's another area that we can do priority research in to really understand whether it offers any promise at all or not. We need to improve our observations and monitoring, and we saw in a previous talk how important that is for the UK. We need to understand these environments, how they behave, how they're interacting, how they're changing, and that's really going to be critical. And as scientists, we need to provide objective evidence. The science that we produce is really needed by policymakers and regulators. It's needed by industry and the people developing these technologies. And so as we move from exploration to exploitation, this information is more and more in demand. And we need to make sure that we're providing objective evidence to feed into these discussions as marine scientists. At the moment with deep sea mining and other disturbances as well, you see this huge spectrum of different views. You see some people talking about the wonderful world with more sustainable critical minerals that we can all use for our smartphones and electric cars. And the Prime Minister, a little while ago, one or two since, saying how it could be a big boon to Britain. And then on the other side, we have people saying it's going to be an environmental disaster. And the reality is that the current uncertainty doesn't really allow us to distinguish very clearly between these two views. And we need environmental information, we need information about the mining, and we need a lot of other information to do that. We need to make sure that we engage in discussion with the key stakeholders, and we need to be really transparent in the way that we do that and encourage this open dialogue. We've seen examples where science already influences these decisions on a very broad scale. particularly through the International Seabed Authority and the meetings they have, but also through nation states and other mechanisms as well. We've seen examples where science was used to create the network of APEIs in the first place, and we've seen a responsive change. We've seen additional APEIs, so additional protected areas being added to the map to encompass gaps in our scientific understanding. When we showed that nodules were important for these communities, an additional API was put in an area with high nodule density. So we can make a difference already. And we see this cycle of continuous improvement, and this is a sort of thing that we can think of ourselves, but also through the industry, where you get data, you try and understand it, you make predictions, you carry out activities, and then you reassess. And this continual improvement cycle is going to need a lot of scientific evidence throughout the process. We've also seen that deep sea mining is an area of a lot of controversy. There's some extreme views. We've had protests against marine scientific research. This was Greenpeace interacting with one of our recent scientific expeditions. But I feel like the advancement of this scientific knowledge in the area is really important for everyone. It's really important for us to understand, but it's also important for the stakeholders to really make sure that they get the right information and they can make the right predictions about what's going to happen. And we hope that the information that we can produce is objective and repeatable and can be used by everyone. In fact, after interrupting our expedition, they've subsequently used the data that we collected on this expedition as part of a campaign where we demonstrate the number of species in the area, and it's a clear example of the fact that this information is useful for everyone, including the NGOs as well as the mining companies. So in conclusion, we know that deep sea disturbance is increasing. We know that there's these potentially major effects and very slow recovery. We need to do a better job. We need to collect more information, we need to make it available, and we need to do that in a way that's clearly objective. We need to make sure that we're producing open data, we're publishing openly, and we're doing so without influence from the people funding this work, particularly if they have some sort of vested interest either way. UK science has had an important role in this, and I think it's really critical that we move forward in a way that where we're producing this data, we have a once-in-a-generational opportunity to influence the way that this industry and probably others are carried out in a way that protects the environment as much as is possible, whilst still providing some of the benefits from the resources that we get. So with that, I'll say thank you very much to our funders from the Natural Environment Research Council, for the Metals Company for providing data and JPI Oceans, and for the science and seagoing team, many of you which are in the audience today. So thank you very much.